Hello guys, welcome back to our channel. In this series of CFX course, this is lecture number 2. In today's lecture, we are going to study the parametric study and how to optimize the design by using some Ansys rules along with the Ansys CFX. In the last video, we have analyzed a simple static mixer in which the mixing material was the water. So that was a simple mixer in which the hot water was mixing with the cold water. So in today's video, we will optimize this mixer to have the best flow rate of water and the inlet diameter. So these two things we are going to analyze today. We will use some of the Ansys tools along with the CFX to analyze the flow behavior and to get the maximum efficient points. So let's start. So we are using the same geometry and all of the other details are the same. So to start, first of all, launch the Ansys workbench. Also see what we are going to learn today. We will build up the geometry by using design modeler of the static mixer. Then we will set the parameters of the inlet diameter. So if I import the geometry directly into the design modeler, we cannot set the parameter because it is in the step format, and the design modeler does not have the direct, like you can say, the editing is not feasible. So the design modeler cannot be changed the diameter or any of the geometric parameter. So after doing that, we will do the parametric study. So what is the parametric study? Basically, the parametric study is to analyze the different parameters. Like I am going to select the inlet diameter. So instead of having the 0.1 centimeter, I will say the diameter of the inlet is 0.2, 0.25, 0.3, 0.35 or 0.33 meter. So these are the different diameters I want to analyze to see what will happen at the outlet or in the mixer. So instead of using it again and again, like opening the geometry design modeler and editing the geometry and doing all of the process again and again, I will just define it as a parameter and will define some of the desired points that I want to get the where I want to get the results, and whatever I want to get in the results, I will define that, and then I will set up the parametric study, and the software itself will calculate all of the points and then give us the results. So it is very useful technique to optimize the results and to save the time. So also we will gonna learn some of the other tools like the design of experiments. We will use this, and also we will use optimization, which will be based on the response surface. So let's start. First of all, go to first of all go to the toolbox and drag and drop the flow CFX. Okay, now right click and click on new design modeler geometry. Okay, so first of all, check the units, set it to centimeter, choose the ZX plane, click on sketch. Now go to sketching tab. Here you can choose different types of the geometric pattern according to your geometry. I am going to use this circle to build up this. So I want, okay, so now the circle is exactly on the axis point. So let's define the dimension. So our circle has the size of 200 centimeter. It's fine. Okay. Click on generate. Now click on the extrude command, apply, click on the direction and click on both symmetric, define 100 centimeter, click on generate button. I think the Size is 50 centimeter. Now, so one thing you want to, if you see, when I'm using bow symmetric, he will add 50 centimeter to each side. He will not, like, the total will be the 100 centimeters. The total size is 1 meter now. Okay, so now I want to add the outlet. Okay, again go to constraints, choose coincident. Okay, define the diameter. Also you have to check. Okay, it's trying in the same sketch, but we do not want to. Okay, we have to define the new sketch. Okay, now we are going to sketch, doing the sketching in the sketch 2. Okay, define a circle. It's on the center. Okay, it's fine. Click on dimension. Delete it. Click on 20 centimeter. Okay, also click on constraints, make it coincident. Come back to modeling and then click again on extrude. Click on apply and change the condition to reversed. Want to extrude it to 80 centimeter, so it's fine. Also change the diameter to 30. Now it's fine. Okay, now we have to build up the inlet and outlet, sorry, in hot inlet and cold inlet. So we will go to the XY, click on a new sketch, sketch 3. Again use the circle command. There's some problem. Let just 1 second. Again define the new sketch. Look at, oh okay, there was a problem with the sketch plane. Show body. Go to sketch 4. Click on the circle. Coincident. Define the diameter to 20 centimeter. centimeter. Okay, again click on extrude to 110 centimeter. Okay, again click on sketching, create new sketch, sketch 5. Click on the circle. Okay, go to constraints, make coincident, define the dimensions, define it 30 centimeter. Okay, now define the distance to 50 centimeter. it's fine. Extrude, click on the direction and click on reversed. Okay, so we have done with the geometry. So to do the parametric study, we want to choose which of the dimension, like I can study the radius of this static mixer, or inlet outlet diameter, or the length of the static like the inlet pipe or outlet, cold inlet pipe or cold outlet inlet hot inlet pipe, or I want to study the outer diameter or the length, or I want to study the size. We have to choose a parameter. So let's see, you can see this check mark. Basically when I will click on it, so I can define the parameter, but for now I am not going to use this one. I am going to analyze the sketch. I am going to analyze this inlet diameter. So I will just click on the D1 and the pop-up window will come. So I am going to name this parameter as called inlet D. Okay, click on OK. So we have defined one of our input parameter. After setting it, now we have to create the mesh. Okay, so in this case I'm just going to build up the rough meshing. So it's done within seconds. So let's define the name selections. Okay, select the face control and then choose this face. Create name selection called inlet. Also define this hot inlet. Outlet. Okay, so all done. Just click on the update meshing, close this window and come to the setup. Delete the default domain. Right click on flow analysis, insert new domain, fluid. Okay, choose the location. We have only one domain in this case. Come to the material section and define the water. Okay, also the buoyancy model has to be enabled to see the gravity effect. The gravity is working in the negative y-axis. The reference temperature is 300 Kelvin. Okay, it's fine. So now go to the fluid models, use thermal energy, and also for the turbulence I'm using the shear transport model. Okay, click on OK. So it's fine now. Now come to the expression, right click and insert expression. Name the expression hot flow. Okay, so I am gonna use the variable mass flow average 1500 kilogram per second, and now I have to define the location. hot inlet. Click on apply. Okay. Oh, fine. I do not need to write it like this. Just write it 1500 and define the unit kilogram per second and all. Okay, click on apply. Now go to outline again. Okay, insert the boundary, hot inlet, choose the location, use mass flow rate, use expression, define the static temperature to 315 Kelvin. Click on OK. Now define the cold inlet, same mass flow rate 1500 and at the temperature of 285 Kelvin. Okay, now define the outlet, relative pressure is 0. Click on OK. So I will tell you how why I define the hot flow with the expression instead of just defining it in the boundary condition. Okay, all done. Close the window of the CFX and click on solutions. Click on double precision. I am going to use the maximum processor of my computer. Okay, start run. It will take some time, let it be finished, and I will see you again. The simulation is run, so we have got the converged solution at 100 iterations. So next step is to see the results. We have already discussed about the how to plot the contours and streamlines in the last video. So in today's video, our main focus is on the parametric study. So just click on apply and you can see the pattern. Okay, so to do the parametric study we have to define some of our output parameters. So let's come to the function, the equation, insert expression, out temperature average. Okay, so we are going to see the outlet average temperature. So I'm going to use the function mass flow average variable, that is temperature, and we want to see it at the outlet. Okay, click on apply. So we have created the equation. Now we have to define it as output parameter for the workbench. So it's being defined. Now again click on the equation, and I want to see the difference in the temperature at the outlet, like the difference in the maximum and minimum temperature at the outlet. Click on function CFT post max value of temperature at the outlet minus function CFT post minimum value of temperature at the outlet. Okay, click on apply. Also click on it and define it as a output parameter. Okay, all done in this section. Close the window. Now come to the parameter. Now you can see the different parameters are defined here. The inlet size of the cold inlet and output parameters are temperature of temperature average at the outlet, and the difference in the maximum and minimum value of the temperature at the outlet. So what I'm going to use, I am going to use it as variable diameter. So let me define some of the values: 25, 30, 35, 40, okay, or 22. I can define any number within the given geometric condition. Okay, so just now I have to click on update all design points, and all of the data points will be calculated automatically. Click on edit, yes, and you can see the progress here. So now you have to do nothing, just wait for the software and it will do all of the things for you.